Today we're going to talk about Turing machines. First, let's recap some ideas from before. Let's say that A is a set. Recall that P of A, the power set of A, is the set of all subsets of A. Cantor proved in 1891 that the set of subsets is strictly larger than A itself. What this means is there is no surjective map from the set A to the power set of A. The idea is that the proof goes as follows. Let's say that there is a surjective map, call it F, from A to the power set. This means it'll take an element little a in the set capital A and return a subset F of little a that's contained in capital A. Now let's consider the set B, which consists of those elements little a and capital A, such that little a is not an element of the subset F of little a. Even though capital B is a subset, one actually proves that capital B is not in the image of F, therefore showing that if F were any surjective map, we would have a contradiction. This is typically what's called the diagonal argument. As a corollary to this, Cantor was able to conclude that the set of real numbers is not a countable set. That is, there does not exist a surjection from the natural numbers to the real numbers. Using this, we'll say that any set S for which there is a surjective map from the natural numbers to S is said to be countable. You'll notice that if S is a finite set, then it is indeed countable. In fact, if S were an infinite countable set, then this means that we would have a one-to-one correspondence between the natural numbers and the set S. In this case, we'll say that the cardinality of S is Aleph naught. One proves that both the integers and the rational numbers are countable. This means that the cardinality of the natural numbers, or the integers, or the rational numbers, are all equal to Aleph naught. We've seen that the power set of the natural numbers has strictly more elements than the natural numbers. In fact, Cantor's result actually shows that the real numbers has the same number of elements as the power set of the natural numbers. In this case, we'll say that the real numbers is an uncountable set. And actually, we'll say that the cardinality of the real numbers is Aleph sub 1. The continuum hypothesis is a conjecture that says that there is no set S which has cardinality between Aleph naught and Aleph 1. Inductively, we'll define Aleph sub n plus 1 as the size of the power set of a set S that has cardinality Aleph sub n. Russell proved in 1901 that naive set theory, as defined by Cantor, eventually leads to a contradiction. The idea is that one really cannot consider the set of all sets. In some sense, the set is too large. Actually, one can get around this by defining what's called category theory. Indeed, this was really defined to make sure that set theory really has a firm foundation. Today we're going to discuss some ideas from the English mathematician Alan Turing. He was one of the first people to really discuss properties of a computer. In fact, Alan Turing was really motivated by two questions. First, he asked, what is a computer? And second, he asked, what are the limits of what a computer can do? Ironically, he actually found the answers to both of these by looking at Cantor's diagonal argument. We're going to talk about these later, but first let's focus on the first question. We'll say that a computer is a machine that contains programs P such that an input I yields an output P evaluated at I. Turing tried to create a theoretical framework for what a computer should be. He thought of a computer as having two parts. First, there should be a tape, which nowadays you can think of as a hard drive, that should consist of individual cells, which nowadays you can think of as sectors on a disk. Second, he said that there should be a head which can read or write one cell of the tape at a time. Here's a diagram to help emphasize what's going on. Again, there should be a tape which one can really think of as having infinite length. And for this tape, we have individual cells. Each cell should contain exactly one symbol. Next, there should be a head which can either read or write one cell of the tape at a time. You can see here on the diagram that the idea is that the head can move along the tape to the left, to the right, wherever it would like. The head contains instructions, which are our programs P, where if it reads a symbol I in the cell on the tape, then it'll create a new symbol P of I. Alan Turing first described such a device in 1936, calling it an automatic machine and later a logical computing machine. Again, he thought of this device as having an infinite memory. He really didn't worry much about the storage size, but he did say that on the tape, really there's only one symbol at a time, and the head can then scan in the symbol and read it. The tape can then move back and forth. Nowadays, we think of this as having a hard drive, and the needle can move anywhere on the drive it would like. Nowadays, we call such a device a Turing machine out of respect of Alan Turing. Turing was actually computed in the limits of computation, and to this end, he considered the following halting problem. Let's say that P is a program and I is any input. Can one determine whether the program P evaluated at I finishes running eventually or whether it will continue to run forever? Actually, it was Martin Davis who first used the phrase halting problem some 20 years later in 1958. Let's try to make all of this a bit more precise. Let's consider that program halt, which returns true if the program P of I stops running after a finite amount of time, or false if the program P of I continues to run forever. Turing actually proved that such a program cannot exist. In fact, he proved in 1936 that the general algorithm to solve the halting problem for all possible program input pairs cannot exist. Before we try to discuss this in any more detail, let's maybe go over some examples. Let's let P be that program which adds the integers from 0 through a given positive integer I. For example, if I is 3, this program would add 0 plus 1 plus 2 plus 3 and would return the number 6. Then this program in general, P of I, finishes running eventually. That is, in this case, halt of P and I is true. Now let's let P be that program which searches for the word mathematician in a given text document I. Think of this as you may have an email program and you want to use the search feature for your email document to search for the word mathematician. Well, because the email document is of a finite length, then P of I will eventually finish running. That is, in this case, halt of P of I is true. Now, let's let P be that loop which does the following. It will start at 0. It will then add 1 to 0, replace that with a new number, which we'll call n, and then we'll replace n with 1 plus the previous number n. Essentially, at every stage, we're just adding 1 to the integer, and this whole algorithm is independent of the input I. Of course, because we can start at 0, add 1 to get 1, add another 1 to get 2, add another 1 to get 3, we can continue in this way forever. And so we see that P of I is a program that does not terminate. It will continue to run forever. And so in this case, halt of P of I is false. Let's now talk about the proof of the theorem. We want to consider the following program, in which case, here on the screen, we'll write this in pseudocode. The function does the following. Let's say that we have a program P. We would like to evaluate P at the input P and determine whether or not the program P evaluated at P will run forever. Here on the screen, we've written a program that says if halt PP is false, then the program trouble evaluated at P will return true. Otherwise, If halt PP is true, then the program trouble evaluated at P will just run on forever. The whole idea here is that the program trouble simply determines whether the program P evaluated at P will run forever. If P evaluated with the input P runs forever, then trouble at P will return true. If P evaluated at P stops after a finite amount of time, then the program trouble at P will itself continue to run forever. We'll try to prove, by way of contradiction, that the program halt cannot exist. The idea is that we're going to take halt and evaluate it at trouble, and then run into a contradiction. Let's assume for the moment that halt really does exist, and that we indeed can evaluate halt at trouble. The point is that the output only has one of two cases. Either it's true or it's false. Let's say for the moment that halt trouble is true. Remember what halt does. It determines whether the program evaluated at the input stops after a finite amount of time. So if halt trouble is true, then by definition, trouble evaluated at trouble will stop after a finite amount of time. But now let's go back to the way that we've defined our program trouble. Remember that trouble only does one of two things. Either it returns the value true if halt of something is false, or itself will run for an indefinite amount of time. Well, if halt trouble stops after a finite amount of time, then this means that it must have evaluated the statement true. But if trouble evaluated true, then it would have saw that halt trouble equals false. Again, just looking at the definition of our weird program, trouble. This, of course, is a contradiction. We can't assume halt trouble is true, but then have a program that internally would evaluate halt trouble is false. So let's assume the other way. Let's assume that halt trouble is false. Then from the definition of the halt program, this means that trouble must continue to run forever. But now, let's take a look at the definition of the program trouble. The whole point is that trouble will either return the value true or itself will continue to run forever. Well, if trouble continues to run forever, then this means that from the way we've set everything up, halt trouble must be equal to true. Again, we find a contradiction. In either case, we must conclude that the program halt cannot exist because we can't have true is equal to false. Thanks for watching.